Hey everyone, so we're going to continue on with section 6.3. The last section focused on applications of trig, ratios, and basic elementary trig ratios. We learned how to solve for trig ratios within the context of right triangles, which have specific limitations. That was all in section 6.2. 6.3 is going to expand our scope and teach us how we can now solve for trig ratios in more than just a right triangle type of setting. So beforehand we were able to find, say, sine, cosine, tangent, secant, cosecant, cotangent of angles within a right triangle. As you guys know, any of those angles, theta, beta, alpha, whatever they're called, are limited to angles that are less than 90 degrees. So if I already have a 90-degree angle in a triangle, the acute angle that I would be taking the sine, cosine, or tangent of would be an angle that's, let's say, 89.9 degrees, or 80 degrees, 70 degrees, anything less than 90. That's a limitation, right? We know we have angles that can be bigger than 90 degrees, and we saw that when we put an angle in standard form. We can easily have an angle that extends out into quadrant 2. Let's say I have a 120 degree angle. So what does that mean? Does that mean that if I have a 120 degree angle, I can't find the sine of 120? Well, if you punch the sine of 120 into your calculator, you're actually going to get an answer. Okay? So obviously we're not limited to only trig ratios in a 30, 60, 90 degree triangle. So that's what this section is going to focus on. How do we find trig ratios of all angles? So a trig function will be defined as we see on slide 92. Trig functions have theta as a triangle in standard position, and the point P, which is x comma y, can be a point on the terminal side if r equals the square root of x squared plus y squared is the distance from the origin to the point P, which is x comma y. What the heck is this talking about? So firstly, we're defining a point P and a distance r. So let theta be an angle in standard position. So let's say we have, for simplistic purposes, an angle in standard position always starts on the positive x-axis, and let's have this angle end somewhere in quadrant 1, so that this angle is theta, right? We're saying theta is an angle in standard position. Point PXY is a point on the terminal side, so this is the terminal side. Let's say I'm drawing this as the triangle, right? And point P is a point on the terminal side. Let's define that as point P. That point P has an x coordinate and a y coordinate. Now r is the square root of x squared plus y squared, is the distance from the origin to point P. So we're going to define this as r, which is the square root of x squared plus y squared. Now, does that really make sense? Let's think about that. This is point P. Point P, as we know, every point has an x value and a y value. If this point P has an x value and a y value, the x value of the point is represented by the distance traveled here. That's x. Right? So if this was a point, let's say a fake point 3, 4, then we know the only way to have gotten to this point 3, 4 from 0, 0 would have been to go 3 units out and 4 units up. So the x value would be a 3 in this case, and the y value of the point would be the vertical distance traveled, 4 units. So if I had a point 3, 4, then I moved across 3 units and up 4 units. What would be the distance? Well, what would be the distance between point 0, 0 and point 3, 4 here, the distance of this line? Well, we learned that if we have a right triangle And when we discussed the distance formula in chapter 1, this was a shorthand. I said instead of memorizing d is the square root of x2 minus x1 squared plus y2 minus y1 squared, instead of memorizing that formula and saying, okay, I'm going from 0, 0 to 3, 4, we can draw a right triangle, which we already have, and say, hey, look, if one side is 3 and the other side is 4, then the hypotenuse here, or the distance that we call r, would be the square root of 3 squared plus 4 squared. 9 plus 16 is 25. The square root of 25 is 5. So the radius, I'm sorry, not the radius, it will be the radius soon enough. We're calling this the hypotenuse, or the distance r, is 5. And we get that by using the Pythagorean theorem. So what is this whole definitional nonsense telling me on slide number 92? Well, it says the sine of theta is y over r. Well, isn't the sine of an angle the opposite side over the hypotenuse? Yes, it is. What is the opposite side represented by here? The y value of the point. What is the hypotenuse represented by here? R. So it makes complete sense. If I'm defining a point on my terminal side as P, and that P has an x and y value, and the x value is the horizontal displacement, or the distance I traveled from this point to this point horizontally, and y is the vertical displacement, the distance I traveled from 0 up to get there. If this is 3 comma 4, this part would be 3, this part would be 4. And if I wanted the sine of theta, well, so katoa, sine is opposite over hypotenuse, it would be 4 over 5. But that's in my pretty little example with 3, 4, and have a 3, 4, 5 right triangle, a Pythagorean triplet. If I didn't know what the value was, if I just had x, y, it would be y over r. So that's the sine of theta. What's the cosine of theta? The cosine of theta is the adjacent side over the hypotenuse, x over r. What's the tan of theta? Well, TOA, opposite over adjacent, it's y over x. And again, where x and y are the x and y coordinates of that point. R is the distance between the origin and that point. And all of these things can be solved for. So we can see these relationships more clearly by drawing out a unit circle. That's the point that I have on the bottom of the slide. I'm going to draw out a unit circle for you. We're going to go over unit circles a bit more when we're in chapter 5. I don't like the unit circle approach to trig, but I didn't really invent math, I just regurgitate it. So I'm going to show you what the unit circle is all about. But I'm going to show you why I like chapter 6's approach to trig a bit more. But these trig ratios that are defined on that slide, on slide 92, are very important. We're going to be able to utilize those ratios to solve for trig ratios in any quadrant, whether they're angles that are smaller than 90 or bigger than 90, and we'll see how to do that soon enough within this section. Slide 93. If we're given trig functions as defined on slide 92, we can draw a unit circle to make some sense out of trig ratios. So what is a unit circle? A unit circle is a circle with a radius of 1. So if I go out 1 unit in each direction, 1, negative 1, negative 1, positive 1, and draw a circle, okay, that's a unit circle. A unit circle has a radius of 1. So r equals 1. Okay, any radius that I draw out. Now, we can use this unit circle to basically map out any terminal point. If this is one side of my angle, and let's say this is another side of my angle, this angle theta would be formed between the initial and the terminal side. I can draw a perpendicular down here to have a right triangle formed. Now on the slide I used points A, C, and B as this triangle, right? So I had, and let me blow this triangle out a bit, points A, C, and B here, where this was theta, the angle that was formed in my unit circle. Now I know, since this is a circle with radius 1, the hypotenuse is going to be a 1. Right? That's the radius. That's what r equals. I don't really know what the other sides are, but I know that the sine of angle theta is equal to the opposite side, which is side BC, over 1. Because it's opposite over hypotenuse. The cosine of theta is equal to the adjacent side, AC, over 1. The tan of theta is opposite over adjacent, BC over AC. Now the reciprocal functions, secant, or let's start with cosecant, because cosecant is the reciprocal of sine, starts with an S, starts with a C, so it would be 1 over this value, or just the reciprocal of that value, 1 over BC. Secant of theta would be 1 over AC, because it's the reciprocal of cosine. Cosine starts with a C, its reciprocal function starts with an S. And cotan is the reciprocal of tan. So let me write cotan out here. Cotan of theta is AC over BC. Alright? So if I have this context written out here, this can be very useful. And I have here, we can use the unit circle to find the value of trig ratios at 0 degrees, 180 degrees, 270 degrees, 360 degrees. That's the extent of usefulness of the unit circle in my experience. Using it for other angles is more involved than using a triangle approach. So I think this unit circle and the definitions that we have on the other slide are useful in certain cases. Let me tell you what those cases are. Okay? So what's one case? Let's say I'm asking you to find the sine of 0 degrees, or the cosine of 0 degrees. Well, how would you go about doing it? By the unit circle method, the sine of an angle is equal to the opposite side over the hypotenuse. Since the opposite side, right, is equal to whatever the opposite side is, BC, and the hypotenuse is equal to 1, I can just say, hey look, it's the opposite side, BC. Now, if I gave this a point, let's take slide 92's perspective, if this was a point x comma y, well then, wouldn't the y value of this point, this y value, be the height of the triangle? Like we had in the prior problem, if this was 3 comma 4, that means that this side length is 4. Yeah, that would be the case. So what I see here is the sine of theta is actually the y value of the point. BC is the y value of point B. That's what BC's length is equal to. If this is 3 comma 4, the length of BC is just 4. So the sine of this angle is equal to the y value of that point. The cosine of this angle is AC over 1, which is just AC. That's equal to the x value of point B. Weird. So what this is telling me is, if I have a point that lies on a unit circle, anywhere on a unit circle, right? Any point that lies on a unit circle, and I had an angle that was formed by the initial side and the terminal point was ending anywhere on the unit circle, The x value of that point would be the cosine of the angle theta. The y value of the point would be the sine of the angle theta. So x is cosine of theta, y is the sine of theta. Because the cosine of theta is adjacent over hypotenuse, and AC over 1 is just AC, and AC is the length that is associated with the x value of this point. Whatever the x value of the point on the terminal side was. So again, from our prior example, if this was 3, 4, if that was point B, which it isn't, obviously, because that made the radius 5, so it doesn't fit within this context. But just to give you a small example, if this was 3, 4, then we know r would be 5, but that would mean that the length of this piece of the triangle was a 3, and the cosine of theta would be 3. But we know now we're in the unit circle, so I can't use the point 3, 4, right? This will actually expand itself to circles of any radius, so it is useful even outside of this scope. That's why with 6.2 on slide 92 we started with the sine of theta is the y value over r. But here, in a simplified approach, if we're just using a unit circle, that's why I say the unit circle is very useful for evaluating something like the sine of 0 degrees. Now, what would the sine of 0 degrees be? Well, if I drew out a 0 degree angle, that would be the initial side here and the terminal side right on top of it. It doesn't go anywhere. That terminal point has a point on the x-axis of 1, 0. We know that the sine would be, since it's a unit circle, the sine is the y value of the terminal point. So the y value of the terminal point is 0. So the sine of 0 is 0. The cosine of 0 would be the x value of the point, 1. And you can verify this on your graphing calculator. If you're in degree mode, what is the sine of 0? 0. What is the cosine of 0? 1. And let me give you another couple of examples. In this same problem, what would the tan of 0 be? Well, the tan of 0 was BC over AC, so it's the y value over the x value. So here the y value is 0, or the sine of 0. The x value is the cosine of 0, which is 1. So the tan of 0 would be 0 over 1, which is 0. And that's how we find sine, cosine, and tangent of 0 degrees. We can use the unit circle to say, hey look, this point on the unit circle, if I had the starting and ending point, would be 1, 0. The x value of the point corresponds to the cosine of the angle. The y value corresponds to the sine of the angle. Tan would be y over x. And we can use any of the reciprocal functions similarly. So cosecant would be 1 divided by the y, 1 divided by sine. Secant would be 1 divided by x. And cotan would be x divided by y. So any of those points would help us. Let's say I wanted to find the sine of 90 degrees now. Well, for the sine of 90 degrees, the initial side is here again on my xy axis, but now my circle ends right here. The terminal point would be at 1, 0. So what I would look at for a 90 degree angle, since the terminal point is on the point 1, 0 of the unit circle, the sine of 90 would be the y value of this point. The y value of 1, 0 is 0. That's the y value. The cosine of 90 would be the x value of the point. That's a 1. The tan of 90 would be y over x. Right? So the tan of 90 would be what am I messing up here? Oh, I'm sorry guys. This is not 1, 0. This is 0, 1. It's y why I'm a little off here. And I realized it when I got to tan. So this is 0, 1, sorry. So the sine of 90 is the y value, it's a 1. The cosine of 90 is the x value of the point, a 0. So when I get to the tan of 90, which is why I realized I made a mistake, I have 1 divided by 0. Because it's y over x. The y value is a 1, the x value is a 0. We can't divide by 0, so the tangent of 90 is undefined. And we'll see that when we get to the graphs of tangent, sine, and cosine. And again, all of this can be easily verified on a graphing calculator. But the way that I used to test this stuff would be to force people to algebraically show me, hey, if I gave you the tan of pi over 2, or the cosine of pi over 2 translates to 90. If I had the cosine of 90 degrees, I would be asking you to draw out a unit circle indirectly and giving me the x value of the point at 90 degrees. And similarly, we can go on for other angle measures that are on the axes. So I claim the usefulness of the unit circle is at 0 degrees, 90 degrees, 180 degrees. So if I asked you for the sine of 180 degrees, cosine of 180 degrees, or the tan of 180 degrees, again, I would look at the point value, it's -1, 0. The sine is the y value of the point on the terminal point. The y value is 0. The x value is a -1. So if you type in cosine 180 or cosine pi on your graphing calculator, you should get a -1. Tan would be y over x, 0 over -1, which is 0. You can do the similar exercise for 270 degrees. 270 degrees again ends on an axis. So here, as you can see, the reason why I'm saying these are useful is because I can't really draw a triangle. If I have a 270 degree angle, I can't draw what is going to be known as a reference triangle, which we're going to learn about in a few minutes. So any of these four values, 0 degrees, 90 degrees, 180 degrees, 270 degrees, it's useful for me to think of the trig ratios of these angles, and I'll do cosine of 270 just as an example. At 270, we're looking at the x value here. The point here is 0, -1, so the cosine of 270 would be a 0. So this unit circle helps me and gives me an understanding of the trig ratios from the prior slide, saying, look, if I draw out a triangle, I understand that by Pythagorean theorem, whatever terminal point I have, x comma y, since the radius is 1, the sine of this angle would be the y value divided by 1, which is just the y value of the point, because anything divided by 1 is itself. The cosine of the value is the x value of the point. Cosine of the angle is the x value of the point, because adjacent over hypotenuse gives me adjacent over 1, which is just the adjacent side. The adjacent side would be equal to the x value of that terminal point. And everything from there follows suit, because tan is opposite over adjacent. Well, the opposite side is represented by the y value of the point. The adjacent side is represented by the x value of the point. So I have y over x. And everything else is a reciprocal function, so it's 1 divided by something before. So I think that's unit circles, and that helps me understand sine, cosine, tangent, secant, cosecant, cotangent of 0, 90, 180, 270 degrees, and other iterations of 90 degrees, whatever ends on an axis. So 360, 360 plus 90, which is 450, 450 plus 90, which is 540, anything that ends on one of the axes, any angle that ends on one of the axes, I can find the trig ratio of that angle by drawing out a unit circle. Slide 94. So 6.2 teaches us to solve for trig ratios within a right triangle. This limits us to angles under 90 degrees. So this was talked about in the intro to this section. This section, 6.3, introduces us to the unit circle methodology, which helps us evaluate trig functions at any degree. Now, we're still going to use right triangles. That's the key here. But we're going to relate an acute right triangle, right? A right triangle with a angle with other angles that are less than 90 degrees, obviously, to those obtuse angles, to the bigger angles that we're asked to find the trig ratios for. It's like saying, okay, I have something in one currency, I want you to convert it to another currency. Or another example would be, I want to find the value of something based on a true indicator, right? So give me like a really good hint or a clue. So it's like, I call it like an ugly cousin. That's what we're going to call the reference angle. So we're going to judge what somebody's what somebody's character traits are based on the character traits of their friends. It might not always, necessarily work out in the real world, but here, within the context of evaluating trig functions, that's what we're going to do, and it's going to help us. So, to evaluate trig functions at any angle, we first need to see whether our function will yield a positive or a negative result in the quadrant that we're working in. So I give you a quadrant breakout. Quadrants 1, 2, 3, and 4, and what angles are positive in which quadrant. So this is going to be step one of our thinking, okay? So let's break it out. If I have an angle that ends in quadrant 1, right? So let's say I have an angle that ends in quadrant 1, any angle. If I draw a right triangle that is representative of that angle, I know that the x value is going to be positive and the y value is going to be positive, because it's on the positive x-axis and positive y-axis. A hypotenuse is always positive because it's the square root of this squared and this squared. So if I'm squaring this and squaring that and adding it, I'm always going to get a positive result. So the hypotenuse is always positive. But if I take any trig ratio of theta in quadrant 1, whether it's sine, cosine, tangent, cosecant, secant, cotangent, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, or any of the reciprocal functions are always going to be positive because everything is positive. So here we put an A for all trig ratios are positive. Now what if an angle ended in quadrant 2? Right? We start here, we draw an angle that ends in quadrant 2. Let's say a 150 degree angle. Well, this 150 degree angle that ends in quadrant 2, technically, I can't draw a right triangle for it, right? But I know that in quadrant 2, if I use that unit circle approach that we defined on the first slide of 6.2, I would have to look at the xy value of this point, and the x value of the point would be negative. The y value would be positive. So you can think about it as, even if I draw like a little mini triangle here on the flip side, which is what we're going to end up doing actually, and that's going to be your reference angle, but I don't want to get too far ahead. But if I have a negative x and a positive y, and I just said that the x value represents the cosine of theta, well, I'm showing you that the cosine of theta that ends in quadrant 2 is going to be negative because the x value is negative. The sine of theta is going to be positive. The tan of theta, since it's y over x, positive over negative, it's going to yield a negative result. Now the reciprocal of sine is 1 over a positive number is going to be positive, so cosecant is positive. Secant is going to be negative because 1 over a negative is negative, and cotan is going to be negative as well. So we see that since a point in the second quadrant, in quadrant 2, so this was quadrant 1, right here, that's quadrant 1, going counterclockwise, we go from quadrant 1 to quadrant 2. In quadrant 2, since the x values are negative, cosine, tangent, secant, and cotangent are negative. So the only thing that's positive is sine and its reciprocal function cosecant. So we see here, I have a quadrant breakdown, quadrant 1, 2, 3, and 4. In quadrant 3, similarly, an angle that falls into quadrant 3, let's say 220 degrees, that angle falls into quadrant 3. If I draw out the complete circle, well, this x value is negative. The x and y value of the points are both negative and negative here. So x is negative, y is negative. That means cosine is negative. Sine is negative. Tan, since it's negative over negative, is going to be positive. And the reciprocal functions follow suit. So here, tangent and its reciprocal function, cotangent, are positive. And finally, in quadrant 4, let's say I have a 315 degree angle. The point here is going to have a positive x but a negative y. So cosine is positive. But sine and tangent and their reciprocal functions are negative. Because the y value is negative, sine is y. So sine of theta is y. Sine of 315 would be a negative. And tan of 315 would be a negative over a positive, so it would be negative as well. So we have a little mnemonic, right? If you're going from quadrants 1, 2, 3, and 4, if my angle ends in quadrant 1, all are positive. Angle ends in quadrant 2, only sine is positive. Angle ends in quadrant 3, only tan of that angle is positive. And angle ends in quadrant 4, only cosine of that angle is positive, and obviously all the reciprocal functions. So ASTC, right? So there are a bunch of different ways to remember this, and this is again phase 1 of our thinking. First, if I have the cosine of 350 degrees, I need to figure out, is that going to be a positive or a negative value before I actually find the value, all right? So before we could evaluate cosine of 315, we first need to think, is that going to be positive or negative? And I'm telling you, if you remember ASTC, 315 ends in quadrant 4, so the cosine of 315 will be positive, right? How do we remember this? In high school, all students take candy, all students take calculus. For my college students, all strippers take cash, all students take crack. I don't care. However you want to remember this, remember it, right? But ASTC is how you do it, okay? Phase 1 is whatever angle my quadrant, whatever quadrant my angle falls into, I need to remember, is it going to be positive or negative in that quadrant? Is the trig ratio of that angle going to be positive or negative in that quadrant? That's phase 1 of the journey. What's phase 2? So slide 95, we also need to know what the reference angle is going to be. Let theta bar be an angle in standard position. Let theta is a typo. Let theta be an angle in standard position. The reference angle theta bar associated with theta is an acute angle formed by the terminal side of theta and the x-axis. What the heck is going on, right? And then I say to evaluate a trig function, find the reference angle theta bar, determine the sine of theta, which is what we did on the prior slide, and find the value of theta except for maybe this sine. So I have this little picture here as well. It looks like a butterfly or a bow tie. And that picture is indicative, and that picture being this picture here, of what the reference angles are within the 4 quadrants. What am I talking about? Well, let's look at the definition clearly. if I have an angle that ends in quadrant 1, let's say I have a 50-degree angle. The definition of a reference angle is an angle theta bar associated with theta, which is the acute angle that's less than 90 degrees, formed by the terminal side of theta and the x-axis. Well, where's the terminal side of this angle? That's this side. Where's the x-axis? Right here. So, oddly enough, theta bar here is also going to be 50 degrees. Theta is 50 degrees. Theta bar is 50 degrees. Okay? Now, if I had a 410 degree angle or a 400 degree angle. So, for a 400 degree angle, that gives me one complete revolution of 360 plus another 40 degrees. So what would the reference angle be associated with a 400 degree angle? Just the angle formed by the terminal side and the x-axis. So the reference angle, theta bar, would be 40 degrees. So quadrant 1 should be in the bag for you guys. If I need a reference angle in quadrant 1, it's just the angle formed by the x-axis and the terminal side. What about quadrant 2? So if I had an angle that ended in quadrant 2, let's take 130 degrees. 130 degrees ends in quadrant 2. The initial side is always on the x-axis, positive x-axis. What is the terminal side? This is my terminal side. Now, theta bar is defined. Let's look at it again. The reference angle theta bar associated with theta is the acute angle formed by the terminal side, that's this, and the x-axis. Well, this whole thing, my friends, is the x-axis. I'm not going to go back to the positive portion of the x-axis. I'm going to go to the x-axis here because it is the acute angle. I'm not going to go back here because that's 130 degrees. Acute means less than 90. So theta bar here completes out or is supplementary to this 130. Theta bar here is also equal to 50 degrees. So what does this mean? That means an angle that ends in quadrant 2 will have a reference angle that sort of completes it. A reference angle that goes from this terminal side down to the x-axis. So if I had to take the sine, cosine, or tangent of 130 degrees, I would use 130 degrees' ugly cousin. I would use 50 degrees. So if I have an angle bigger than 90, like 130, that ends in quadrant 2, I would use the angle that is supplementary to it, that sort of completes the cycle to 180, by drawing an angle from the terminal side to the x-axis. Let's look at quadrant 3. Similar type of thought process. Let's say I have an angle that goes into quadrant 3, like 225 degrees. 225 degrees is angle theta. That's the official angle. Well, what angle would go that is acute from the terminal side here to the x-axis? Well, that is this portion of angle theta. So it's a part of the original angle. In fact, it is the part that goes above 180, but it is less than this given angle. So theta bar would be 45 degrees here. So in this case, it's 225 minus the 180. So this extra little blurb, because that goes from the terminal side to the x-axis. So again, if I had to find the sine, cosine, tangent, secant, cosecant, cotangent of 225 degrees, I would use 225 degrees as ugly cousin, 45 degrees, to help me. That's the point of the reference angle. We take a big angle that cannot fit in a right triangle, and we find an acute angle that's related to it. It's sort of the way in, right? It's giving us the fake ID. We're finding a way into the club, all right? If I have a 130-degree angle and I need to get in, but it's bigger than 90, so they won't let me in, I need something that's related to it that is less than 90. And 50 is going to be the golden ticket. If I had a 225-degree angle, I could not do sine of 225 with a right triangle that has a 225-degree angle. It's not possible. But we're going to see that we could relate a 225-degree angle to a 45-degree angle. And the process is on the same slide, slide 95, right? So I'm going to ask you, let's find the sine of 240 degrees together. How are we going to do it? The process is written out on the slide. The sine of 240 degrees. Well, my hint to you is always, firstly, let's draw this out. So I'm going to draw this guy out. 240 degrees goes above 180, and it goes into this quadrant, into quadrant 3. That's theta is equal to 240 degrees. My hint to you is, again, I won't be able to find the sine of 240 degrees because I can't draw a right triangle in it. I can't do SOHCAHTOA. I can't see opposite over hypotenuse with a triangle that has a 240 degree angle. It doesn't exist. Triangles are maxed at 180 degrees. So what do I have to do? Well, I need to find 240 degrees' relative. So I'm going to find the reference angle formed by the terminal side and the x-axis. That's this piece right here. That piece, theta bar, happens to be 60 degrees. So 240 degrees is related to 60 degrees somehow. Now let's see if we can wrap out the relationship. My claim is that I can find the reference angle associated with theta, determine the sine of theta by seeing what quadrant it lies in. Well, quadrants 1, 2, and 3. If I go by all students take calculus, only tangent is positive here. So the value of theta is the same except for maybe the sine as theta bar. Sine of 240, since it's in quadrant 3, is going to be negative the sine of 60. That's the trick. The sine of my obtuse angle is going to be either plus or minus the sine of the reference angle. The sine of the big angle is going to be either plus or minus the sine of the reference angle. And that's why we find reference angles, and that's why we bother to see, firstly, is it positive in the quadrant that it's in, or negative. And we can test all of this on our graphing calculator, by the way, but first, let me find minus the sine of 60. Now, my whole reason for doing this was saying, hey look, if I find an angle that's less than 90, I can now find a reference angle, draw out a triangle. Yes, you can. If theta is now 60 degrees, and I have a right triangle, then what's the sine of 60 degrees? It's the opposite side over the hypotenuse. In a triangle that has a 60-degree angle and a right angle. Hold up. We had special triangles that were 30, 60, 90 triangles. I told you this would show up again. The ratio of sides of a 30, 60, 90 triangle, opposite the 30 is x, opposite the 60 is x root 3, and opposite 90, or the hypotenuse, is 2x. So if I wanted the sine of 60, it would be opposite x root 3 over hypotenuse, 2x, but it's negated. It's a minus sine of 60, so I put a minus in front of it. I can factor out the x over x, and I get a minus root 3 over 2. That would be the right answer on a final for my class. if you had to find the sine of 240 degrees, you would find 240 degrees is relative by drawing it in standard position and seeing that the reference angle is 60 degrees, and then drawing a triangle to say what would the sine of 60 be. Well, I can find the sine of 60 using a standard special triangle that we learned last class, 30, 60, 90 triangle. Now, a big hint to you, most of your calc and pre-calc professors will be giving you iterations of angles that can allow you to draw either a 30, 60, 90 triangle or a 45, 45, 90 triangle, because we want to see you do the work algebraically. And that's why those two special triangles are so important. If I gave you the sine of 240 or the cosine of 240, in reality, you would make that a reference triangle that's a 30, 60, 90 triangle. Because 180 from 240 would give me a leftover piece of 60. It would have been the same if it was 180 plus 45. If I had the sine of a 225 degree angle or the cosine of a 225 degree angle. So I can extend the limits of a 45 degree angle outside of quadrant 1. I can put a reference angle that's 45 degrees in quadrant 2. Let's say if I had a 135 degree angle. Well, a 135 degree angle goes into quadrant 2. And the reference angle associated with 135 degrees, if theta was 135 degrees, its relative would be 45 degrees here in quadrant 2. 225 degrees would be the relative in quadrant 3 here. So you see what I can do now? I can expand the scope of a regular 45, 45, 90 triangle by giving you 135 degrees or 225 degrees. Or if I went 315 degrees, the reference angle here would be 45. So 315 degrees. They're all allowing us to test you on the same right triangle, but since it's in a different quadrant, different trig ratios would yield either a positive or a negative result. You could always check this work on your graphing calculator. Sine of 240, if you punch that into your graphing calculator, you'll get a weird decimal. Do minus root 3 over 2, you'll get the same weird decimal. So you could always check your work. But the goal of this is always going to be, you're given a big angle, draw it. See what small angle is related to it. It's going to be the same relationship, but maybe off by a minus sign. Instead of a plus, it might be a minus. Remember, all students take calculus, you'll be fine. If you want to remember the dirtier versions of it, you can. Whatever helps you. Alright? But the sine of 240 here is equal to minus the sine of 60. There's another problem here. Let's look at the cosine of 2 pi over 3. I want to do that. Actually, we'll do the full one right underneath it. So if we had secant of minus pi over 4 plus cosine of 2 pi over 3 minus the tan of 180. So we got a full review here. A lot going on. I'm going to run through this problem because you guys can re-YouTube this. The wonders of YouTube. Secant of negative pi over 4. Well, pi over 4 times 180 over pi is a 45 degree angle. But negative pi over 4 means I'm not going counterclockwise, I'm going clockwise. Negative 45 degrees goes this way. Well, theta bar, or my reference angle, is the angle formed by the terminal side on the x-axis. It's actually 45 degrees. So that is my reference angle. It's my reference triangle. Negative 45 degree angle is equivalent to a positive 45 degree angle, but maybe off by a plus or a minus sign. Well, let's see. Is secant positive or negative in quadrant 4? This is all students take calculus. cosine is positive here, and the reciprocal function secant is positive here. So secant of minus pi over 4 would be equal to positive the cosine of 45 degrees. Great. I can now find the cosine of 45 degrees, and since the secant of 45 degrees, since cosine is positive, and again, correction, secant of negative 45 degrees is the same as the secant of positive 45 degrees, because the reference angle is 45. Since it ends in quadrant 4, I'm off by a plus or minus sign potentially. Cosine is positive in quadrant 4, so is its reciprocal function secant. So secant is positive in quadrant 4. Now, what is the secant? If cosine is adjacent over hypotenuse, secant is the hypotenuse over the adjacent side. And it's a 45 degree angle. So if we remembered our 45, 45, 90 triangle, we remembered the opposite side is x, the adjacent side is x, the hypotenuse is x root 2. So cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. So the secant of 45 degrees is x rad 2 over x. The x's factor out, so I just get a plus rad 2. That's the first part of 3 parts. What's the cosine of 2 pi over 3? Well, 2 pi over 3 times 180 over pi. Pi's cancel. 3 and 180 gives me a 60 times 2 gives me a 120. Great. Cosine of 2 pi over 3 is the cosine of 120 degrees. 120 degrees is bigger than 90. Let me draw it out. Let me find my reference angle associated or affiliated with it. 120 ends in quadrant 2. The affiliated reference angle with 120 degrees is 60 degrees because it's between the terminal side and the x-axis, and it's acute. So theta bar is 60. Great. So if theta bar is 60, then the cosine of 120 should be plus or minus the cosine of 60. It depends. Is it positive cosine or 60 or minus? Well, here everything is positive. Here only sine and the reciprocal function are positive. So if I need the cosine of 120, it's not going to be plus the cosine of 60, it's going to be minus the cosine of 60 degrees. Alright, so let's find the cosine of 60 degrees. This is the triangle in that quadrant. Here's my 60 degree reference angle. Right? And hey look, it's a 30, 60, 90 triangle. Again, 120 is another iteration of a 30, 60, 90 triangle because the reference angle is 60 degrees. Opposite side is x root 3. Adjacent side is x. Hypotenuse is 2x. So what's the cosine of 60? Cosine of 60 is adjacent x over hypotenuse 2x. But I need to negate it. So I get minus 1/2. So far I have plus rad 2, minus 1/2. What's the last piece? Minus the tan of 180. Well, let me draw this guy out. 180 degrees. Hey look, that ends on an axis. I'm going to use the unit circle. The unit circle approach, right, tells me that the x value of the point is cosine of theta. The y value of the point is the sine of theta. Well, what's the xy point value of 180 degrees? The point here is negative 1, 0. I went negative 1 out, 0 units up. So the cosine of 180 is negative 1. The sine of 180 is 0. The tan of 180 is y over x because it's opposite over adjacent. We have to look back at those formulas and remember them, but it's the y value over the x value. 0 divided by negative 1. And that gives me a 0. So overall, I have rad 2 minus a half minus 0, which is rad 2 minus a half. And that's how you could leave the answer. On an exam, that's how you would have left the answer back in the day, when we got tested on things like this. Okay, so you're going to get plenty of practice problems on this through homework and web work. If you have any questions, you should definitely reach out. But again, the general consensus is when I get an angle that's in another quadrant, whether it's a negative angle or whether it's a bigger angle that is bigger than 90, I want to create a relative of that angle if it falls into another quadrant. If it falls on an axis, I want to use a unit circle approach and use the xy value of the point to get that value. So this problem sort of brought the whole section together. 96. So trig identities, this is something that we're definitely going to cover more in chapters 7 when we're discussing different relationships between trig ratios. You have all of them on the slide. What I did was at least give you some of the identities that are also found in your textbook. And you can use some of those relationships now to help you. You can see that we're using, let's say, to find the cosecant, 1 divided by the sine, to find the secant, 1 divided by the cosine. So I don't need to get into that. We've discussed that those are reciprocal. For the tan of theta, we saw that the tan of theta is y over x, where y is the sine of the angle and x was the cosine of the angle. When we go deeper into the unit circle approach, and I put up a similar diagram to what I already put up on the board today, you're going to see this relationship a bit more clearly, but it's another relationship. The Pythagorean identities that come underneath as well are definitely identities that we're going to stress more in detail in chapter 7, and I'll show you more with the unit circle how they come to be when we go through stuff in chapter 5. The next slide, and the last slide for this section, slide 97, the area of a triangle. Not really a major focus for this class, but way back when in kindergarten we learned that the area of a triangle, a standard triangle, right? If I can draw a triangle and draw a height down, the area of a triangle is 1/2 base times height. That's something for your crap ad exams, stuff that you really need to remember. But this is all fine and dandy. What happens if I have an obtuse angle? So I gave you a picture here. What if we have an angle theta like this? What would the height of this triangle be? So we'd have to actually extend out the base and down the height, because we need the height of the triangle to be perpendicular to the base. So this height of the triangle would be outside of the actual triangle itself, which confuses some people, right? But we'd have to calculate that height. Long story short, you have the definition here. If this was A, and this was B, and this was height H, the area of this triangle would be 1/2 AB times the sine of theta. Right? And again, this is not something that I'm holding you guys to. Really, it's not very important in my mind for calculus. For your crap ad exams, memorize the formula. It's nothing that's, I believe, heavily tested at QC, or probably not going to see this in the future. Almost always, when they test area of a triangle, it's your standard area of a triangle. But this is a special formula for obtuse triangles, right? That's slide 97. I know we sort of ran through the last two sides fairly quickly, but we're going to definitely get into more depth on slide 96 within later chapters. Try your web work problems, try your homework problems. If you have any questions, always feel free to reach out. Good luck.